The first law of thermodynamics. In the previous video, we covered the sign convention for heat and work in a thermodynamic process. In this video, let's take a closer look at concept of heat and work in a thermodynamic process. Work done during volume changes. Suppose we have a quantity of gas, which will be our system, and our system is enclosed in a cylinder with a movable piston. We apply pressure on the piston, compressing the gas from initial volume V1 to final volume V2. The piston moves from initial position to final position. We have the resulting volume change in our system. You will recall our equation for work is integral of force F dotted with dx, meaning if we apply force and the object undergoes displacement x, there's a corresponding work done. Pressure is basically force applied on the area of the piston. So basically, we are applying force on the piston, and the piston moves from initial position to final position. There's a corresponding displacement. Therefore, there is a corresponding work done. Piston is F over A, basically. If we apply that equation for pressure into a if we apply that or put that equation of pressure into our equation of work, we get the work done during this volume change. Work is equal to integral of pressure P dV from initial volume V1 to final volume V2. And depending on the pressure and the volume change, you have different equations or values for the work done during the volume changes. For instance, if pressure is 0, then 0 work done. If there is no volume change, the resulting delta V is 0, there is also 0 work done. If the pressure P is constant, it is put outside the integration and we are only integrating dV. Consider now the following pressure versus volume graph, which gives us four different states: state 1, state 2, state 3, and state 4. Let state 1 be our initial state and state 2 be the final state. Going from initial state 1 to final state 2, we have three different paths that the system can take. There's the path 1, 4, 2, and then there's the path 1, 3, 2, and then there's the direct path of 1, 2, 2. So we have three different paths that the system can take from initial state to final state. And as you shall see, the work done by the system will depend on the path taken. So first, let's take a look at path 1, 4, 2. So the system goes from state 1, then state 4, and then final state 2. From state 1 to state 2, the volume is constant at V1. No volume change, which means no work done from initial state 1 to state 4, even if the pressure is not zero. Zero work done because constant volume. Going now from state 4 to state 2, the final state, the volume changes from V1 to V2. The pressure is constant at P2. So constant pressure, we take the pressure P outside the integration. So we are simply integrating dV. The equation for work will give us work is equal to P2 times V2 minus V1. So from initial state 4 to final state 2, the work done by the system is P2 times V2 minus V1. Zero work done. Work done W. Total work done therefore is P2 times V2 minus V1. Going now to the second path, path 1, 3, 2. So from initial state 1, you go to state 3 and then to final state 2. From initial state 1 to state 3, the volume changes from V1 to V2. Constant pressure at P1. This gives us work done from 1 to 3 to be P1 times V2 minus V1. From state 3 to final state 2, the volume is constant, zero work done. Therefore, the total work done from initial state 1 to initial state 2 is P1 V2 minus V1 plus 0. Total work done is P1 times V2 minus V1. Familiar. The equation is familiar. It has the same form as the previous path. But instead of pressure P2, you have pressure P1. So different work done since P1 is not equal to P2. Finally, we have the direct path from initial state to final state. We have path 1, 2. The pressure changes and the volume changes. Therefore, the work done is equal to integral of P dV from initial volume V1 to final volume V2. You have three different paths. Depending on the path taken from initial state to final state, you have different values or equations for the work done by the system. So in determining or calculating or analyzing the work done by the system from initial state to final state, you need to consider the path taken by the system from initial to final states. The same goes for heat added in a thermodynamic process. Just like work, the heat added to a thermodynamic system when it undergoes change of state depends on the path taken from initial state to final state. Consider two different cases representing two different paths. So two different cases but same initial state and final states. Case 1, you have a gas in a container with a piston. So you have a container with a piston, with a movable piston, and inside the container is our system, the gas. Initially, the gas has a volume of 2 liters. If you now heat up the gas using a stove, Heat from the stove flows into the gas, and the gas expands, performing work on the piston, so pushing the piston up, reaching a final volume of 4 liters. Here, heat flows into the system, therefore Q is not zero. The gas performs work on the piston, the work done is not zero. If we now take a look at the second case, you have a gas in a container. Total volume of the container is 4 liters, but there is a breakable membrane that confines our system, the gas, to this half of the container. So 2 liters, the volume of the volume of the gas is 2 liters, the initial volume of our system. If the breakable membrane is broken, the gas will naturally expand to fill up the new volume. Final volume is 4 liters. Since no heat was added, Q is 0. The gas naturally expands just to fill up the remaining volume of the container. So 0 work done. Initial state 2 liters, final state 4 liters. Initial state 2 liters, final state 4 liters. Same initial and final states, but different heat added in the thermodynamic process. In case 1, Q is not 0, but in case 2, Q is equal to 0. The two cases have same initial and final state, but depending on how the system went from initial state to final state, there are different values for Q. So just like work, you need to take into account the path taken by the system from initial state to final state when calculating or analyzing heat added into or flowing out of the system. That's it for now. In the next video, we'll talk about the first law of thermodynamics. So thank you for watching.